What if the Big Bang wasn't the beginning? A groundbreaking physics hypothesis claims our universe was actually born inside a black hole. And this week, 900 scientists might have just proven it's true. Published in Physical Review D, this model changes everything we know about cosmology. It claims our Big Bang was not a beginning, it was a bounce. But for that hypothesis to work, one impossible condition has to be true. Dark energy, the force that has been pushing the universe apart for 11 billion years, cannot be constant. It has to be fading. 15 million. That is the number of galaxies a team of 900 scientists just mapped to track the history of that expansion. And what they found does not fit the standard model. Not slightly off, not within the margin of error. Two independent teams, different instruments, different data, different methods, reached the same conclusion in the same week. Dark energy appears to be weakening. The bounce cosmology hypothesis did not predict this result. It required it. And the universe just delivered it. This is what they found. In 1998, two independent teams of astronomers were doing something routine. They were measuring how fast the universe was expanding using supernovae, stars that explode with a predictable brightness, cosmic rulers. They expected to find that expansion was slowing down, gravity pulls. Everything in the universe is pulling on everything else. The Big Bang sets space in motion, and that motion should be decelerating under the weight of everything that exists. Instead, they found the opposite. The universe is not slowing down, it is speeding up. Something is pushing. Something is winning against gravity on a cosmic scale. They called it dark energy. Not because they understood it, because they needed a name for something they couldn't explain. Einstein had a slot for it. In his equations of general relativity, there is a term called the cosmological constant, lambda, an energy uniformly distributed through all of space. Constant density, constant pressure, everywhere, at all times. Lambda is repulsive, it pushes space apart. In the standard model of cosmology, dark energy is lambda, the energy of the vacuum itself, empty space, quietly humming. Theoretically, that makes perfect sense. Quantum mechanics predicts that even in the absence of matter, space is not empty. It contains fluctuating fields, virtual particles appearing and vanishing. Here is the problem. When physicists calculate what that vacuum energy should be from first principles, the answer is 10 to the power of 120 times larger than what we actually observe. Not 10 times, not 1,000 times, 10 followed by 119 zeros. This is the largest discrepancy between theory and observation in the history of science. Imagine predicting the temperature of a room will be hotter than the core of a star, and walking in to find it at exactly 21 degrees Celsius. Something is cancelling almost all of that energy. We do not know what. We do not know why. In March 2025, DESI published its results. The Dark Energy Spectroscopic Instrument, mounted on a 4-meter telescope in Kitt Peak, Arizona, capturing light from 5,000 galaxies simultaneously. In 3 years of operation, spectral data from nearly 15 million galaxies and quasars, objects spread across 11 billion years of cosmic history. The goal was specific. If dark energy is lambda, a true constant, the expansion rate should follow a precise, predictable curve. The same push, always the same, a line that does not bend. When researchers combine the DESI map with data from 3 independent sources, the cosmic microwave background, supernovae, and gravitational lensing, the standard model struggled to fit all 4 datasets simultaneously. But a model where dark energy changes over time, where its influence weakens as the universe ages, fit the data well. What we are seeing is deeply intriguing. It is exciting to think that we may be on the cusp of a major discovery about dark energy and the fundamental nature of our universe. Alexei Lotho-Harnett, DESI co-spokesperson. The signal, 4.2 sigma. In physics, 5 sigma is a confirmed discovery. At 4.2 sigma, the probability this is random noise is 1 in 40,000. But here is what should actually disturb you. DESI was not alone. The same week, a second collaboration published independent results. The Dark Energy Survey, 400 researchers, different instruments, different sky coverage, different methodology, different data entirely, same direction, same conclusion. Both teams found hints that dark energy is not constant, that its strength appears to be fading as the universe grows older. It's interesting that things are pushing in this direction and that multiple experiments are seeing some tension with the idea that dark energy is constant. Michael Troxell, Duke University, Dark Energy Survey. We are much more certain than last year that this is definitely a thing. Seshadri Nadatha, DESI collaboration. 2 independent experiments, both stronger than last year, both pointing the same way. If dark energy is weakening, the fate of the universe is no longer what we thought. The standard model predicted a specific ending, eternal expansion accelerating without limit, every galaxy receding beyond every other galaxy's horizon. An eventual universe of perfect isolation, every particle separated from every other particle by a distance light can never cross. Not a collapse, not a bang, a permanent, silent expansion into emptiness. That future depends entirely on lambda being constant. If dark energy is fading, if its push is diminishing, gravity may eventually slow the expansion. And under certain models, if dark energy continues fading toward 0, the contraction that follows would compress the universe back toward conditions that resemble those from which it emerged. If you watched Tuesday's video about gravitational bounce inside a black hole producing our Big Bang, this matters. That hypothesis requires a universe that does not expand forever. It requires a universe that eventually reverses. And that reversal requires dark energy to either fade or reverse sign. The DESI data does not confirm bounce cosmology, but it removes one of the standard objections to it. If dark energy is not lambda, then it is something else. 3 possibilities, each more unsettling than the last. The first, quintessence, a dynamic field filling all of space with a density that changes as the universe ages. Unlike lambda, quintessence has a direction. It evolves, it can weaken, it can potentially reverse. The second is more disturbing, not a new ingredient, but a failure in the theory itself. General relativity has been tested to extraordinary precision. Every gravitational wave detection, every black hole image, every solar system measurement, it passes every test. But those tests are local. The DESI measurement spans 11 billion years. At those scales, no test of general relativity has ever been performed with this precision. It is possible that Einstein's equations, correct everywhere we have checked, are not precisely correct at cosmological scales, and there is a third possibility: the cosmological principle, the assumption at the foundation of all modern cosmology, that the universe looks the same from every location, in every direction, at large scales. If that assumption is even slightly wrong, if the universe contains large-scale structures our model ignores, then the DESI signal might be a measurement artifact. We're in the business of letting the universe tell us how it works, and maybe the universe is telling us it's more complicated than we thought it was. André Coussou, Berkeley Lab, DESI. In 2026, the Nancy Grace Roman Space Telescope launches. It will survey a field of view 100 times larger than James Webb per image. Its primary mission includes measuring the expansion history of the universe at a precision that will either confirm the DESI signal or eliminate it. If Roman confirms it, the cosmological constant as we defined it is wrong. Lambda, the term Einstein added and then called his greatest blunder, the term cosmologists later reclaimed as their best explanation, would need to be replaced by something we do not yet have a name for. If Roman rules it out, if the DESI signal fades with more data, then lambda survives, and the vacuum catastrophe remains, a prediction 10 to the power of 120 times too large, with no explanation for why the universe chose the precise value it did. Either outcome changes something fundamental. 15 million galaxies, 11 billion years of expansion, 2 independent teams pointing the same direction. The universe does not owe us a fixed answer, but it is giving us a better question. Between them, the Hubble tension, still unresolved, James Webb finding structure forming too fast in the early universe, DESI finding expansion not following the predicted curve in the late universe. These are not isolated anomalies. They may be different expressions of the same missing piece. Drop your answer below. Do you think dark energy is weakening, or is this a measurement artifact? I read every comment. Subscribe to Untold Universe. Tuesday, Thursday, Saturday.